Hello, hello. My name is Zachary Booker, and this is Lab 5. And not only Lab 5, but the final lab of Physics 2212. It's been a great term, and let's end it very strongly with magnetic braking with Faraday's Law. And obviously, it's by me, Zachary Booker, a third year mechanical engineering student. For anyone who's watching this great lab, the purpose of this lab. So, let's cover the purpose of this lab, and let's first go over things that we might need. So we're going to need Faraday's and Lenz's law, whereas Faraday's law is defined as the change in flux of is equal to the magnitude of the change in flux is equal to the magnitude of the integral in E dotted by a change in distance. Basically, what this is saying is that over a magnetic field can induce a current over its area, which is a very good observation. It's very useful and leads to some very interesting models, such as falling magnets, which is what we're doing today. We're also going to need Biot-Savart's law. In order for us to calculate a flux, we're going to need a magnetic field. This equation refers to a point, but for a more accurate model, we may need to use um, a magnetic dipole in order to make our calculation more accurate. Or if you have a magnetic ring, then it will be more accurate to use the equation for a ring. Or if you have a coil, it'll be more accurate to use the equation for a loop and multiply by n amount of coils. Also, let's get back to the lab. Another thing about this lab, we will have to collect and measure data observed from a magnet falling through a cylinder of aluminum foil. As always, we'll create a computational model of this motion via glow script. And here's our data. The measurements of our aluminum foil was 0.312 meters. The inner radius was 0.014 meters, and the thickness was 0.008 meters. The mass was 0.24 kilograms, and the magnetic dipole moment was 1.57. And here are my times for my data set. Actually, I wasn't ready. But over my data, I was able to see that my average clocked into, I would say, around 1.3 seconds. So here's my computational model with my lab on glow script, and all these components of this lab are used to replicate Faraday's law, which is, the falling magnet and creating a flux, and exchange of flux inducing a current. And this is another example of my computational model. You can see a picture of my magnet. You can also see the velocity plotted against time. You can also see more lines of my code right here. This is a calculation of the magnetic force and the gravitational force of the magnet. The time results in 1.285 seconds. What if the resistivity of the conductor were reduced as close as possible to zero? What would be the effect on the motion? My answer was that the velocity would be near constant. But if holes or slots were cut into the tube, how would this affect the ring's currents in your model? Well, I believe that the magnet will fall faster. It's been a great semester, and this has been Zachary Georgia Booker, and I love this course, and good luck to everyone in the test on Tuesday.